So we were doing the first principle of induction still, and I've introduced to you the Fibonacci numbers. So the Fibonacci numbers is what's known as a recursively defined sequence. So you have this function fn. F of 1 is 1, f of 2 is 1, and then for n bigger than or equal to 3, f of n is the sum of the two Fibonacci numbers previous to it. So fn is fn minus 1 plus fn minus 2. So if we want to make this little table of values here, n is 1, 2, 3, all the way up to 9. F of 1 is 1. F of 2 is 1. F of 3 is 1 plus 1, 2. F of 4 is 2 plus 1, which is 3. F of 5 is 3 plus 2, which is 5. F of 6 is 3 plus 5, which gives you 8. F of 7, 5 plus 8, 13. 8 plus 3, 21. 13 plus 21, 34. All right, so let's prove that. So I wanted to use, I had it here earlier, it was Fn is greater than 1.4 to the n for all n bigger than or equal to 6. So the base case here is 6. Let me check, make sure that's right. 1.4 to the 6. Yeah, okay. All right, so the base case here is n equal to 6. Now, the Fibonacci numbers has a little bit of a hitch in it, in that when you refer to Fn, you're not only referring to Fn minus 1, but you're also referring to Fn minus 2. So not only do you have to go one step back, like with most induction, you actually have to go 2 steps back. Okay, so in actuality, you need to look at the base case for two different numbers. Okay, so in the base case, we'll look at n equal to 6 and n equal to 7. You need to go back 2 steps rather than just 1. So it's a little sort of technicality in dealing with the Fibonacci numbers. All right, well, when n is equal to 6, Fn is equal to what? We've got it up on the table there. When n is equal to 6, Fn is equal to
8.
8. And then 1.4 to the n is equal to, well, it's 1.4 to the 6th power, which is 7.52, right? And 7.52, is less than 8. So that works out. And then for n equal to 7, well, Fn is equal to 13. Yeah. And 1.4 to the n is 1.4 to the 7, which is 10.54. And 10.54 is less than 13. 10.54 is less than 13. So it works out for n equal to 6 and n equal to 7. Now for the induction step. Again, there's a little bit of a technicality involved with the Fibonacci numbers. in the definition of the Fibonacci numbers, let's take it with us so we can look at it while we're working. So definition of Fn, f of 1 is 1, f of 2 is 1, and then Fn is Fn minus 1 plus Fn minus 2 for n bigger than or equal to 3. So that's the definition of Fn. So in the induction step, actually, you need two statements in your induction hypotheses. You need to assume for one step back and for two steps back. Okay, so we will assume that Fn minus 1 is greater than 1.4 to the n minus 1, or to the n minus 1 for n minus 1, for some n minus 1, bigger than or equal to 6, and assume that Fn minus 2 is bigger than 1.4 to the n minus 2 for some n minus 2 bigger than or equal to 6. So two assumptions, because we need to work with two versions of Fn. And we want to show that Fn is greater than 1.4 to the n is true as well. Okay? So, we want to show Fn is greater than 1.4 to the n. All right. What do we know about Fn to start out with?
We know it equals f of n minus 1 plus f of n minus 2.
Yes. What is the reason for that?
The definition.
That's the definition of the Fibonacci numbers. Right? So that's by definition, and because n minus 2 is at least 6. Right? Because it has to be n bigger than or equal to 3 for that sort of thing to work. By definition, Fn is equal to Fn plus 1 plus Fn plus 2. So now what? What do we know about Fn minus 1 and Fn minus 2? What did we assume about those?
That they were larger than 1.4 raised to the n minus 1 and 1.4 raised to the n minus 2 respectively.
So this sum is greater than what?
1.4 raised to the n minus 1 plus 1.4 raised to the n minus 2.
Oh, okay. Now we're trying to work our way up to 1.4 to the n. So what might I do now? We're trying to show that Fn is greater than 1.4 to the n. So far, what do we have? We have Fn is greater than 1.4 to the n minus 1 plus 1.4 to the n minus 2. How can we work our way towards 1.4 to the n? Is there some way I can get a 1 to the n out of this expression here?
You could combine the two, couldn't you?
How do we do that?
Which that would be. Oh.
It's almost there. What else do I need here? Is this right? What I've written here? It's not.
No, it's not. I'm just trying to.
What do I have to do
to make it
fix
right.
that? It's x to the a plus b equal to. What can you do when you have a sum in the exponent? Pre-calculus, guys. This is pre-calculus.
Yeah, this is what happens when I forget to go back and restudy algebra on a regular basis.
It's x to the a times x to the b.
Yeah, exactly. So can we apply that here?
Okay, yeah, so raise the two that you don't already have marked to the -1 and the -2.
Exactly. Right? -1 and -2. All right, so this is 1.4 to the -1 plus 1.4 to the -2 times 1.4 to the n. What's this equal to here? Let's see. 1.4 to the -1. Oh, I've got the. Should have the. There it is. Plus. No, that's not right. So 1.4 to the -1 plus 1.4 to the -2. $1.2244. So this is equal to 1.2244 something something times 1.4 to the n. Last step. What are we trying to show?
That f of n is greater than that.
Greater than 1.4 to the n. So there's just one step left here. By the way, what am I doing? Am I stacking my inequalities or working in a chain?
Working in a chain because you don't have something on the other side of the inequality, which implies it's just
right. Oh, we forgot to do something here. What was the reason for this one here? This part was by the induction hypothesis. You have to mention when you use the induction hypothesis. So, at any rate, this equal to, let's do more of a line here. Cut, paste, equal to this. Equal to this. So far I've got that Fn is greater than this. And I want it to be greater than 1.4 to the n. Can I just conclude that at this point?
I kind of want to say yes, but at this point it's obvious, but I got a feeling there's still something you have to say.
No, it's obvious. It is obvious. Well, it's obvious. At this point, it goes without saying. When you multiply something by a number bigger than 1, what happens to it? It gets bigger or gets smaller?
It's larger.
Yeah. So if I take away that multiplier, it gets smaller, right? So what can I write here? It's greater than 1.4 to the n. This is bigger than 1. And this is whatever. All right, so 1.2 apples is greater than 1 apple. All right, 1.2 apples is greater than just 1 apple, where the apples are these things. Okay, so that's another example of an induction proof using inequalities. Let's look at it again. So we want to prove that the Fibonacci number Fn is strictly greater than the exponential expression 1.4 to the n for every n bigger than or equal to 6. Okay, now it's a little bit different than other induction proofs with the first principle induction, because you actually have to do 2 base cases and 2 induction hypotheses, because with the Fibonacci number Fn, you don't just refer to the number 1 before it. You have to refer to 2 numbers beforehand, 1 and 2. So in order to deal with F100, you don't just deal with F99, you have to deal with F99 and F98. Okay, so you got to go back, instead of 1 step at a time, 2 steps at a time. But still ordinary induction. So with n equal to 6, Fn is 8, 1.4 to the n is 7.5, for n equal to 7. Fn is 13, 1.4 to the n is 10.5, and they both satisfy the desired inequality. Now, assume Fn minus 1 is greater than 1.4 to the n minus 1. And Fn minus 2 is greater than 1.4 to the n minus 2. For some n minus 2 bigger than or equal to 6. Now show that Fn is greater than 1.4 to the n using these 2 hypotheses. So we start with one side of that inequality, Fn. By the definition of the Fibonacci numbers, Fn is equal to Fn minus 1 plus Fn minus 2. We assumed Fn minus 1 is greater than 1.4 to the n minus 1. Fn minus 2 is greater than 1.4 to the n minus 2. So by the induction hypothesis, this sum is greater than this sum. This sum is equal to this sum, just using that identity x to the a plus b is x to the a times x to the b. So that's 1.4 to the negative 1 times 1.4 to the n plus 1.4 to the negative 2 times 1.4 to the n. Factoring out 1.4 to the n looks like that. And then this is just 1.2244 something something times 1.4 to the n. This number is bigger than 1. So if I remove it and replace it with a 1, then this 1.22 times 1.4 to the n is bigger than 1.4 to the n. And that's what we wanted. Fn is greater than here and greater than here, 1.4 to the n. Again, when you're working with inequalities, you must work in a chain. You cannot stack inequalities. It doesn't make sense. Okay? You have to work in a chain. I mean, suppose I was to write this. So by the induction hypothesis, Fn is greater than 2 to the n minus 1 plus 2 to the n minus 2. Oops. So Fn is greater than 2 to the, not 2, 1.4 to the n minus 1 times 1.4 to the n minus 2. So this is greater than 1.4 to the negative 1 times 1.4 to the n plus 1.4 to the negative 2 times 1.4 to the n. So Fn is bigger than 1.4 to the minus 1 plus 1.4 to the minus 2 times 1.4 to the n. So Fn is greater than 1.22 like that. All right, well, how does that make sense? I mean, in this case, it kind of does. But think about it. It kind of does because this left-hand side stays the same. The right-hand side is what changes. The right-hand side is what changes. Okay, so it makes sense in some way. Okay, but what sort of what sort of reasoning is required to think about it? Well, this is the case. Why? This was what? This equality. That's
By
definition.
definition.
Okay. So this, is somehow by the induction hypothesis. How does that hold by the induction hypothesis?
It doesn't.
Well, I mean, it does in a way. I mean, if I was to write something like this, A equals B, so A is bigger than C. Suppose I was to write this, A is equal to B, so A is bigger than C. So A is bigger than D. So A is bigger than E. I mean, suppose I was to write this. I mean, here we've got some numbers to look at, but now look at this. If I was to write A is equal to B, therefore A is bigger than C. Why would that be the case? Why would it be the case? There's only one reason why this could, A bigger than C, could follow from A equal to B. There's only one reason why.
If B was known to be bigger than C?
If B was known to be bigger than C. Yes, that's the only reason. So if B was known to be bigger than C, then from A equal to B, one can conclude that A is greater than C. But why don't you just write this? That leaves no question. Now suppose I was to do this. Suppose A is bigger than C, therefore Z is bigger than D. Under what conditions would that be true?
D would have to be equal to or less than C, and Z would have to be equal to or greater than A.
Right. But I mean, which is it? I mean, you don't know from what I've written here. You would have to think about it at each step. So, I mean, rather than saying any kind of junk like this, it's easier to say X is bigger than or equal to Z, is equal to A, is equal to B, is bigger than C, is bigger than D, is equal to E. Therefore, X is bigger than E. This says the whole thing all in one go. There's no need to think about anything more. All right, this simply, is doesn't make sense and requires more explanation than you can provide. I mean, if it were to make some sense, it needs more explanation than you can provide neatly in a stack like that. Okay, inequalities are done in a chain, always. Sometimes there are sort of sub-chains within the chain, but, that's fine. The basic idea is that you work in a chain. Okay, so no stacking inequalities. Okay, you got to work in a chain. With at each step in the chain, you say, how it follows. This equality is by definition, this is by the induction hypothesis, and then this is all just pre-calculus, so you don't need to say anything. All right. So we've done quite a few examples of induction working with equations. But induction has a lot more usages than just dealing with, these algebraic identities. There's lots of issues, especially in combinatorics, in theoretical computer science, in geometry, that deal with induction. Statements that don't seem to be about induction, but they actually are. So here's a nice example. So a collection of lines, L, on the two-dimensional plane are said to be in general position when every pair of lines in L intersect but no three lines in L intersect at the same point. So nothing like this happens. Okay, so every pair of lines intersect, but no three lines intersect at the same point. It doesn't happen. Notice that if L is in general position, and H is in L, then L minus H, so I take that collection L and I take out H. Is it still in general position? Every lines besides H intersect in a point, and no three lines aside from H intersect in the same point.
Yeah, it's still in general position.
Yeah. It's still in. Any subset, actually, will still be in general position. Right? In fact, if H is a subset of L, then the lines of H are still in general position. Okay. Let's take a look at something. Okay, so one line in general position. What's it look like? It looks like that. Right?
Can one line even be in general position?
Yeah. It satisfies every pair intersect, and no three, every triple doesn't intersect. Every pair intersects and every
if
triple.
If the hypothesis is there's a pair, and the hypothesis is false, it'll still be true. Because there's no pair.
Right, it's a vacuous statement in that case. Every pair intersect. Okay, I don't have any pairs. Okay, so the statement every pair intersects is true. If I don't have any pairs, that's the vacuous statement. If the implication, if the hypothesis is always false, the conclusion is always true. Or not the conclusion. If the hypothesis is always false, the implication is always true. So one line. No, notice what do I get here with one line? I get one region one, or two regions. I get this plane split into two regions, region 1, region 2. What about two lines? What's that look like? Well,
4 regions.
Yeah, only the angle varies, right? But then I get, region 1, 2, 3, and 4. What about three lines? What's three lines look like? Well, two lines looks like that. There's no variation except in the angle. But I'm not really concerned about the angle. What's the third line got to do?
Add 3 more regions.
No, I mean, it either does this, makes a triangle like that, or it makes a triangle like that, but that's really the same thing. Right? How many regions do I have now? 1, 2, 3, 4, 5, 6, 7. 7 regions. The plane is separated into by 3 lines in general position. That's a theorem. So let's use the first principle of mathematical induction. To prove that if L is a collection of n lines in general position, well, let's write it not as an if. Oh my goodness. So a collection L of n lines in general position subdivides the plane into n squared plus n plus 2 over 2 regions. Has anyone ever seen this before?
That looks like the number of the triangle.
Well, up here for like 3, for n equal to 3, right? Well, you get 7 lines, right? So when you plug in 3 here, you get 9 plus 3 plus 2 is 14 over 2, 7 regions.
Sorry, the row I was looking for, it looks like the sum of all the integers from like, 1 to 100.
Oh, yes, not quite that. That's n squared plus.
It's not quite, but it looks.
Yes, very close. Very close. Or no, it's n squared. Plus.
It's n times n plus 1
over 2. Yeah.
So
it's not quite that. Yeah. All right. So this is Pn right here. This is the predicate. A collection L of n lines in general position subdivides the plane into n squared plus n plus 2 over 2 regions. Base case. Well, n equal to 1 line. So 1 line yields how many regions?
2.
2 regions. Right? And then n squared plus n plus 2 over 2 is equal to 1 plus 1 plus 2 over 2 equals 4 over 2 is 2. Right? And they're the same. Alright, so 1 line geometrically gives you 2 regions. Right? I mean, there's the picture. 1 line gives you 2 regions. And then this polynomial here, n squared plus n plus 2 over 2, when n is equal to 1, so for n equal to 1, n squared plus n plus 2 over 2 equals 1 plus 1 plus 2 over 2 is 4 halves is 2. Induction step. Pn implies Pn plus 1. Or you could do Pn minus 1 implies Pn minus 1 implies Pn. Whatever your suits your taste. So what is the induction hypothesis? This is Pn right here in the box. Right here in the box, that's Pn. So what's the induction hypothesis? Assume that.
So just be that whole box would be assume a collection L of n lines.
Exactly what's in the box. Yeah. So assume that. I'll shorten it a little bit. N lines in general position define n squared plus n plus 2 over 2 regions. Show that, well, Pn plus 1. What's Pn plus 1?
That n plus 1 lines in general position define n plus 1 squared plus n plus 1 plus 2 over 2.
Define n plus 1 squared plus n plus 1 plus 2 over 2 regions. Okay, before proceeding any further, let's notice that n plus 1 squared, let's simplify this expression. N squared plus 2n plus 1 plus n plus 1 plus 2 over 2 is equal to n squared plus 3n plus 4 over 2. Okay? So just to simplify that expression a little bit. So the number of regions we'll be looking for is going to be that. So what should I do now? Let L be let L be what?
Would you just pick the number you want?
Pick a number that's going to do what we want to do. We want to prove what? We want to prove something about n plus 1 lines.
So just let L be 2?
Sorry? 2?
Would you?
We know something about n lines. Now we want to prove something about n plus 1 lines. So what do we need to analyze? N lines or n plus 1 lines?
N plus 1?
Yeah, so let L be a collection of n plus 1 lines in general position. So we're going to have to finish this next time. But take 1, no, let's not call it L, H in L, and consider L minus H. When I take away H, how many lines do I have left? I've got n lines. What do we know about n lines? N lines give you that many regions. So I have that many regions. Now I'm going to take that line H and put it back in and see how many more regions we get. And it should be that. Okay, so we'll finish.
Okay.
All right, guys. Have a good afternoon, and the assignment is due tomorrow by.
Hi, Professor. I would like to make an appointment, if
Sure,
that's
what
okay.
time? This afternoon I can't meet.
Probably tomorrow morning, if that's possible,
Sure, what time?
around 10.